Continuing Chapter 2, in this next lesson, we're going to look at additional ways to represent data in graphical form. We're going to look at some very good graphical representations, and then we're also going to look at how to build graphs in a deceiving way. Not so much because we intend to deceive, but because we want to be aware of how others can deceive us. So in this section, we'll look at some common and useful graphs, as well as how we can manipulate graphs so that we mislead those interpreting the information. And also we'll look at different ways that technology has influenced how we're able to represent graphical forms. Let's start with a dot plot. A dot plot is a graph for quantitative or numerical data. And if you take a look at this example, we have pulse rates for males, and on that x-axis, that horizontal scale, we have beats per minute. So we have one dot hovering around the 40 label. That means that one of the males in this data set had a pulse rate of 40 beats per minute. We see that above the 50 label, we have two dots, and each dot represents one male. So we have two men in the data set who had exactly 50 beats per minute. And we see that we have some dots in between. So for instance, that dot right here, just to the right of 40, that's probably 42 beats per minute. This is probably 52 beats per minute, 54, 56, 58. So we're jumping by 2 each time. Now, the fact that we have multiple dots stacked vertically over a particular label means that we have multiple readings. So these are repeated readings. For instance, this is, let's see, 60, 62, 64, 66 beats per minute. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 men that had a pulse of 66 beats per minute, if I counted correctly. So here, each one of these readings, we can represent the frequencies or the counts by simply stacking the dots. Essentially, a dot plot is like a histogram. The major visual difference is that instead of bars, we have these dots that are stacked one on top of the other. But if you think back to the uses of a histogram, where the graph allowed us to look at shape and center and spread and possible outliers, the dot plot very much accomplishes that. Dot plots actually have a couple of advantages over histograms. For example, in a histogram, we lost some of the detail of the original data when we grouped data values into classes. Here, for instance, we don't have a class that goes from 40 beats per minute to, like, let's say 48 beats per minute. And so we actually know that there is one reading of exactly 40, one reading of exactly 42, as opposed to saying that there's a total of 2 in this wide class. So again, one advantage of a dot plot over a histogram is that we're actually able to see a little bit more detail of the original data because it's not lost by throwing values into classes. The second advantage is that a dot plot can be built with little to no technology. In fact, dot plots were very popular in earlier decades before computers were common because they could be constructed with typewriters. Now, as I said in my previous slide, dot plots, like histograms, allow us to look at the shape of the distribution of data, and also it does give us a little bit more detail of the original values because they're not lost by grouping them into classes. Another very common type of graph is the stem plot, also referred to as a stem and leaf plot. In this type of graph, we take the original numerical values and we chop off the last digit. And so in this case, we're still looking at pulse rates for men. This is exactly the same data that we saw in the previous slide with the dot plot. And because the pulse rates come in 2 digits, or in some cases 3 digits when we get into the hundreds, we chop off the last digit of each value, and that gets put on the right hand side of these little vertical bars, which are called the stem. So for example, we saw that there was one reading of 40. The 4 in the tens place would go on the left, the 0 in the ones place would go to the right of the stem. So that 4, 0 is one reading. We also saw that there was one male who had a reading of 42 beats per minute. Well, it has the same 4 in the tens place, but 2 in the ones place. So what this does is it naturally groups our values into classes with a class width of 10. So in this first row, we would have all of the values that were in the 40s. Note then that in the second row, we have all the values that were in the 50s. The way to read this is that we had 2 different values of 50 exactly. We had 5 different occurrences of 52. 6 different occurrences of 54, 2 different values that were 56, and so on. So we're able to still see the original values. We're naturally grouping them into classes of width 10 by taking the last digit and placing it on the right hand side of the stem, and then everything else goes to the left. Notice here, for instance, this last row has 2 digits to the left. This reading here would be 102. So it's got the 0 in the tens place, the 1 in the hundreds place, and 2 for its ones place. And then lastly, we have the highest value in this list would be 104. And so very much like histograms, stem plots do have the grouping of data. The grouping, however, happens in classes of width 10 because we're separating different place values in our decimal system. Now let's see if you can imagine that you picked up your computer and you rotated the monitor counterclockwise 90 degrees. What you would have is essentially a stem plot where instead of having dots, now you have those digits. Again, if you were doing kind of the grouping, this is what you would end up with. But more importantly, what you're seeing is a histogram on its side. So if you don't want to take your computer screen and rotate it counterclockwise, maybe take your head and kind of tilt it to the right so that you can see that this is kind of a histogram on its side. If you visualize that, then this here would be our horizontal scale or our x-axis, and then this would be our vertical scale or the y-axis, which is counting frequency. Again, because stem plots are related to histograms, we're able to see the overall shape of the distribution of the data, and we're also able to look at what the original data values were, like we did with dot plots. Another type of graph that we won't spend a lot of time on are graphs that look at what happens with data over time. So we have a time series graph here where time represents the horizontal scale and whatever we're measuring would go on the vertical scale. In this example, we're looking at law enforcement fatalities over the course of the years 1985 to, it looks like 2015, if I'm looking at this correctly. And we see that there was a peak just after the year 2000. And I think if we think back to the events of the year 2001, it's quite possible that this peak that we see right here was due to the fatalities during the aftermath of the World Trade Center towers coming down in New York. In a time series graph, we're basically looking for trends over time. Another type of graph is the bar graph. Now, bar graphs look somewhat like histograms do, but whereas histograms display numerical data, bar graphs are used to display categorical or qualitative data, not numbers. So here in a bar graph, we have categories or labels or names. Because of that, we draw the bars so that they don't touch. Why? Because we don't want to imply that these categories are sorted or are related in any way. It's not a scale, it is simply a grouping. And so we do have intentional gaps between the bars in a bar graph to show that this is categorical data, not numerical data. In a bar graph, we still use the vertical scale to represent the frequencies or the counts, but the horizontal scale, where we write the categories, can be sorted in any way that makes sense or in no way at all. One type of bar chart is called the Pareto chart. This is a bar graph where we intentionally list the category that has the highest frequency first, and then we go through additional categories with decreasing frequencies. The category that has the smallest frequency or the smallest count would usually go last to the right, with the exception of a catch-all category such as other. In a Pareto chart, the idea is that we show the highest frequencies first. These tend to correspond to the more important categories, and then of course the lower frequency categories would go last, meaning that they have less importance. Here is an example of a Pareto chart. Again, a Pareto chart is a special type of bar graph that represents categorical data, and in this case we're looking at different causes of fatal plane crashes. Very morbid examples, I may say. So it says here, pilot error has the highest count, the highest frequency. Therefore, pilot error, we could say, contributes to the most explained cause for fatal plane crashes. Mechanical failures would go next, sabotage, weather conditions, and then we see here that in the other category the frequency is a little bit higher, but it's a catch-all category. So in essence, we have the highest frequency all the way down, decreasing to the lowest frequency, and then this one exception is because it is a catch-all category. We also have a pie chart option for categorical data. Categorical data, again, consists of names or labels, and so because it is not numerical, graphs like histograms and stem plots and dot plots would not apply. But most of us have seen pie charts in the past and have some sense of how they work. Pie charts represent the relative frequencies for various categories, and the size for the different slices of the pie correspond to those relative frequencies. So let's take a look at an example in the following slide. In this case, we have the same information as we did a few slides ago, where we have the different causes for fatal plane crashes. And in that Pareto chart, we saw that pilot error was the most common cause of a fatal plane crash, and the size of the corresponding slice of the pie here very much corresponds with that. We also saw that mechanical failure was the second leading cause, followed by sabotage, and weather was the smallest of all the groups. And then we had that catch-all category of other causes, which is slightly larger, but kind of stood on its own at the last because it was a catch-all category. Frequency polygons are not going to be very common in our course. We kind of just mentioned them here as an alternative. A frequency polygon is essentially a histogram, whereas instead of bars, we simply imagine that there is a dot at the top of each bar of the histogram, the bars are not there, but those dots remain, and then we connect those dots. So it is a variation of the basic histogram that we saw earlier, except instead of bars, we see dots that would be at the very top of where those bars would have been. Here we have an example of a frequency polygon, and you might recall this particular example. We're back to looking at the commute time for Los Angeles, and we might remember that the smallest value in that set was 5, the largest was 90 minutes, and in the first category of the histogram, the first class, we had values that went from 0 to 14, so that 7 was the midpoint of that first class. Well, you can imagine the shadow of the bar that would be right here. In fact, if you have notes printed out, you might want to look back at that histogram. That bar was hovering right here over that 7, and it had a height of 6. Well, we're going to get rid of the bar, but we're going to leave a dot at the center of that top of the bar. And we do that for all the remaining bars, connect the dots, and we have a frequency polygon. An interesting way is we always start at 0 and end at 0 for frequency, because polygons are, of course, two-dimensional figures that are completely closed. So that's the only reason that we stretch out to the horizontal axis, is to kind of close up the figure. They don't represent actual frequencies. In this example, we have two frequency polygons that have been superimposed to do the comparison. If you look back at your notes from the previous sections, we did have some commute times for Los Angeles and also for New York and also for Boise. And so this particular one is comparing the Los Angeles commute times to the Boise commute times. Again, think of this as two histograms that are missing the bars and that we're only looking at the top of each bar. And I think you can see why frequency polygons are so useful. It would be hard to superimpose a histogram on top of another, because then we would have the blending of the shading of the bars. But if we're removing the bars and we're only looking at those dots at the top of the bars, then we actually could have line graphs that intersect each other and wouldn't be too confusing or too hard to make out. Now that we've looked at some of the graphs that are very common and that are readily used in statistics, let's turn our attention to how graphs can be used to manipulate interpretations. In other words, to deceive those who are reading the graphs. One common way to deceive is to have a graph that doesn't start at 0. Whenever we are looking at counts, we start counting with, of course, 0 being a non-count, and we go up from there. But it's a natural starting point for counting. Whenever we start a graph at any other value than 0, it throws off our interpretation. Let's look at some examples. In these two charts, we have exactly the same information. However, the impression that we take in through our eyes is quite different. In this case, we're comparing the occurrence of nausea as a result of taking Oxycontin versus a placebo or a sugar pill. In the first graph, we see that there is considerably less occurrence of nausea with the placebo. In fact, in the placebo, we had an occurrence of about 11% of those people who were giving the sugar pill reported feeling nauseous, whereas with the Oxycontin, we had 23% of those subjects reporting nausea. Well, let's take a look at the second graph. The numbers are identical. With the placebo bar, we are still looking at 11% occurrence, and the Oxycontin bar still represents 23%. Now, why does it look so different than in the first case? because in the first case, that vertical bar did not start at 0, it started at 10%. So of these two, this would be the graph that would be considered more correct, more accurate. The bar on the left is exaggerating the occurrence of nausea. It's saying that OxyContin has an occurrence that seems to be in excess of 10 times the occurrence of nausea in the placebo group, when in fact they're not that dissimilar. It is about twice the occurrence, but certainly not 10 times the occurrence. So that distortion, that ratio of 1 to 2 suddenly gets interpreted by the eye as a ratio of 1 to 10. And so that is the effect of starting with a non-zero scale. This would be considered more transparent, whereas the one on the left would be considered to be more deceitful. Another way to manipulate graphs is to use pictures that don't represent the correct sizes. These are called pictographs. Now, pictographs could be done correctly, could be done in a way that is transparent, but usually when pictographs are used is because there is some hidden agenda, some sort of phenomenon that they're trying to exaggerate. Let's take a look at some examples. In this pictograph, we have two pictures of older telephones. This is from the United States National Security Agency looking at phone records. And it says here that in year 1, we had 151 million. Year 2, 534 million. Well, 151 and 534 have less than a 1 to 5 ratio. I think we could, pretty much say it's closer to a 1 to 4 ratio. So if we're really going to look at that ratio truthfully, then it would take between 4 or 5 of these smaller telephones here. But that's not what we see. If we actually were able to cut and paste, we would see that more than 9 of those telephones would fit in the larger graph. Think of 3 side by side and then either 3 or 4 stacked up. So that 1 to 4 ratio or that 1 to 5 ratio is being exaggerated, and what our eyes are seeing is more of a 1 to 9 ratio or a 1 to 10 ratio. So just because the correct information is written beneath it doesn't make it less deceiving. Again, what we interpret is very, very much influenced by our visual cues. And if the visual cue is telling us one thing and the data is telling us another, the visual cue tends to win out in terms of what we believe. So in concluding thoughts for this section, taking care of data, representing it truthfully, representing it transparently is going to be really important. And so here are some tips on how to do that. If we have smaller data sets of 20 values or less, try using a table instead of a graph, because we may just not have enough data for a graph to do it justice. If we are going to use a graph, make sure that we're using features that are not distracting, that if they are eye-catching, it's because the eye-catching has to do with the correct interpretation, not with misleading information. Don't distort data. Make sure that you construct a graph to reveal the true nature of the data. And make sure that you're spending most of the focus on the data itself and not on the design elements. Now, although we aren't going to cover section 2.4 entirely, in fact, we're going to be looking at correlation and regression in chapter 10, I do want to add a little tidbit here about scatter plots because they are a very common and important graph used in statistics. So we'll go through just 3 quick slides in section 2.4. First of all, let's talk about what a scatter plot is. A scatter plot has 2 axes, a horizontal axis, which is the x-axis, and then a vertical axis, which is the y-axis. Now, in a scatter plot, we're representing paired data. For example, let's say that I had 5 children, and for each child I recorded his or her height and his or her weight. So child number 1 is going to have 2 measurements, a height measurement and a weight measurement. Same goes for child number 2 all the way to child number 5. So I can take the height and the weight for each child and treat that as an ordered pair. Let's say that height is the x value and weight is the y value. If I were to plot those 5 ordered pairs, I would get what is called a scatter plot. Now here is an example of a scatter plot. In this case, we have different weights for seals as compared to the width of their heads. So we have ordered pairs. This dot, for instance, right here that I'm circling with my cursor, the overhead width is about 7.2 centimeters, and the corresponding weight in kilograms is probably about 118. So this comes from one seal. This dot here comes from a second seal. That seal has an overhead width of about, I'm going to say 7.4 centimeters, and the weight is about 158 kilograms. So in this scatter plot, we have 1, 2, 3, 4, 5, 6 seals in total, and each one is giving us 2 measurements. Now, scatter plots are incredibly useful in statistics because they are a graph that help us to explore relationships between 2 different variables. In this case, the variable of overhead width is being visually compared to the variable of weight. Here we have another scatter plot, and in this case we have lots more ordered pairs. Unlike the previous slide where we kind of could detect a relationship between the 2 variables, this one seems, excuse the pun, very scattered. We really can't make out any particular shape. And so when we get to chapter 10 later on in this course, we'll be looking at different ways of describing the relationship between the 2 variables. In this case, we're looking at the height of each president measured in centimeters compared to the height of his or her opponent in centimeters. And probably the reason that we can't detect a particular pattern here is that we don't suspect that there is such a pattern.